Is my presentation visible?
Yes, sir.
Okay. So we were discussing about functions, and we talked about how to use the functions to simplify our coding, and we also discussed about what are prototypes and why we should care about prototypes and how to define a prototype. So okay, so we can continue from there. So why we need prototypes or why we need functions? Functions, first of all, we need functions so that we can reduce the repeatability of any particular code. So if you are using a particular function or a particular code again and again, so rather than repeating the code again and again, you can make a small function and use it, and whenever it is needed, you can call it. At the same time, we discussed that these functions can even be kept in a separate file, so that apart from the main code, if you suppose to you are developing another codes and you need that function, you can use it from the file itself. For that, I told you how to design your own C code, and for that, how to design a header file also. So all this we are doing because we are going to follow C99 standard, which is provided by the IEEE's standards. Okay. So if you don't have any argument in the function, okay, whenever we define a function, mostly we define the function like this. For example, function name, and then we will have this brackets. And apart from that, we will have to define it whether what is the return type. So here I can say return type. Okay, return type, then the name of the function, and then the bracket. So return type can be void, it can be int, it can be float, or any other data type. So return type can be void or int or float or any other data type. Now these return types, actually, if you are not using any argument here, for example, in this bracket you can add some arguments also. So let me just take some arguments and then okay. So for example, argument 1, argument 2, and so on. Okay, so these are your arguments, or you can call it parameters of a function. So if there are no arguments, then we can use void. Okay, so if you are going to design a function which do not have any arguments in particular, then you can go for void also, or we can say empty argument function, otherwise will generate error. Okay, because if you are following C99 standard, then if you are going to define something like this, int any function and empty bracket or no arguments in the bracket, then in that case the C99 standard may generate errors. Okay, so this is a valid function. Void the return type, delay, and void you have specified there. Otherwise, this is an error. Okay, so remember, if you are declaring void and you're not declaring any argument in this, then in that case it is an invalid function. So whenever you need to write a void function, prefer to keep the void there, don't leave it blank. Okay, it will generate an error. Let us just check that particular code. Okay, remember, whenever we are designing any program or writing a program, in that case we will always keep an eye on the options that we have enabled in the program. For example, this is our project. Go to options and then C++ compiler. You are using C language, standard C, and here we have clicked or we have checked required prototypes. Okay, and then apart from that, You should keep an eye on all the standards that you are following or not. Okay, so we are following C99, therefore you are using standard C. Before that it was C89. Okay, and we are going for prototype also. So let us check this program where we were making an LED, or these LEDs high or low. So for example, here we have the prototype. How to know whether it is a prototype or not? Function, and then after that you have a semicolon. So that will define the prototype. And why we are using prototype? Because in the option we have selected required prototype. Okay, and it is good idea, or it is a good practice to keep prototypes in the C program, because in that case you will be following standards. Now after that we are declaring the delay. Okay, so void delay void. Okay, we are not leaving it blank here. Before we may have functions like this, and let me just try to make it. And then wait a second, I have not checked the function. So you have to go to require prototype C++ C dialect. Okay, done. Okay, let me just check here. Rebuild. No, so no error. Okay, but here the prototype is there. Prototype is not matching. Wow, how come? Even when the prototype is not matching, we are not getting any error. How is it possible? Let me just clean, rebuild. Still no errors. How come? I'm just going to comment this. Let me go and try to make it. We are getting error. Okay. So we have the prototype, and prototype should be same as that of the main function. Okay. Let me just check. Okay. Error. Now it's not throwing error. But this is not allowed. Maybe I'm not setting up the project correctly. Something is missing, I think. Wait a second. Optimization low. Okay. Text extra options. No. Encoding. Okay. Mr. C. No. What is wrong in that case? No. Okay. No. I'm not able to configure it where the option is for the void function. I have to cross check it again. Anyway, so remember, never leave it blank. Use, if you are not using any argument, then write void in the void functions. Okay, but here I am not getting that error, because there should be an error. To run optimization is low. Okay, something is missing here. Yeah, something is missing. What I have done wrong? Anyway, I will cross check it and then come back to that code next time. This was discussed. Okay, this was also discussed how to make your main program, and then how to create a header file, and how to create functions, C function for any header file. Okay, even if you go for any other language, be it Arduino or be it any other language. For example, if I just show you what happened. Okay, so So suppose if I just talk about Arduino, no, back, Arduino libraries. And then, for example, these are the by default libraries which are provided by the Arduino. And here you can see inside the header file, okay, inside the source folder, you have the header file. Apart from that, there is a CPP file also. So these two combinations should be always there. That means the header file and the CPP file. So always, you should always create a header file. And if you go through the header file, you will always find the same kind of syntax that we used in the previous lecture. If not defined, keyboard underscore h, that means keyboard.h, then define the keyboard.h. Okay. And then in the CPP or the C++ file, you will have definitions of all the functions and everything that they have created for this particular library. Okay. Now, similarly, we will be using those kind of libraries in our project also. And this, I think I have discussed. Okay. Now, coming to stacks, I have discussed this part also, I believe. I have discussed these parts. Let me check. I have discussed these things. Yeah. Wait a second. Yeah, we have created this delay.c and delay.h file. So this all were discussed in the previous class. Okay. So I shall go ahead with the recursive function. We have discussed recursive function also. And we showed how the recursive function generates error and when you move from one memory location to another memory location. So this was all done. I believe we should start from here. So today, shall we start from the switch controlled LED? So previously we were only using the microcontroller, okay, and we were connecting an LED here, and then we were making this LED on or off. What happened? Hello. Okay. So we were using a microcontroller and then we were making the LED on or off. But here there is no logic behind or no processing which is taking place as such, because here only thing that we are doing is making an output and making it on and off without making any decision on that. So today we are going to look at one more add-on or addition in this particular topic, that is reading the input. So here you have the output. So we will read the input from external world, and based on the reading, whether it is high or low, we will be making the LED on or off. So this part, okay, this part we have done, and we are going to talk about this part today, how to read the switch. So taking input from the switch, remember there are two ways or two techniques which are used to connect a switch with a microcontroller. One is pull up and the other one is pull down. We never leave the pins floating. When I say floating, that means something like this. Most of the time, students or designers, what they do, they use the switch like this. Either they connect it to VCC, this is one option, or they will use switch like this, where the switch will be connected to ground. But remember, when the switch is open in both cases, okay, so this switch, when or this switch, when they are open, they are neither connected to VCC or ground. So if suppose you look at this diagram, then they are not connected. This switch is not connected to either ground or VCC. So these kind of switches or this kind of connections are called floating connection. Okay, and we should never design any system with a floating switch. We should always use either pull up or pull down registers. So here, whenever we are saying pull up or pull down, we are talking about resistors. So we should always use pull up and pull down resistors to connect it to a switch. So if the switch or the GPIO pin is connected to a resistor, and if the resistor is directly connected to VCC, then by default when the switch is open, this pin is getting VCC. So it is high. By default it is high. So we call it pull up. So we are pulling this point or this terminal to up, means high potential. Similarly, if you want to connect it to pull down, you can have a connection like this, where no, this is also pull up. Okay, this is pull down configuration, where we connect the resistor directly to ground. So when the switch is open, you can see the pin is connected towards ground. So this is pull down connection and this is pull up connection. So all the modern microcontrollers and microprocessors, they have this facility by which you don't have to use any external register as such. Rather, they have internal resistances. So this resistance is internal. Okay, so you don't have to connect an extra resistor. You can directly connect a switch because there is an internal pull up register or pull down register available with the GPIO pins. You just have to activate the pull up or pull down functionalities. So remember, the microcontroller TM4123GXL or GH6PM, okay, they have both internal and external pull-ups. Okay, so you can use either the internal pull-up, which is by default provided by the microcontroller itself. You don't need to connect it from external world. Rather, or you can use external option also. Okay, so prefer to use internal pull-up because that will reduce the number of extra components which you need to make a circuit or a system. So going for internal pull-up helps us to reduce the number of components. So this takes reduced number of components, because when you are using external pull-up, you need an extra resistor for that particular connection. Of course, you have to go for the VCC also, which you have to provide from the external world. Anyway, so if you don't have to worry about providing an external VCC or external resistance, always use internal pull-up, okay, which is provided by the microcontroller directly. Okay, so first of all, about the switches and their connection. Now let us look at the schematic of the microcontroller board TIVA C. Okay, we can write it TIVA C board. Okay, and we know that the ports PF0 to PF4 are connected to switches and LEDs. So switch number 2 is connected to PF0. Switch number 1 is connected to PF4. Rest 3 are the LEDs. Okay, now we are going to use those switches. And remember, if you check the schematic which is provided by the company, okay, then in that case you will find that this is the switch connection, where if you press the switch directly goes towards ground. So remember, when the switch is pressed, switch value goes towards ground. Okay, so this thing you have to connect. This thing you have to remember, that when the switch is pressed, GPIO pin is shorted to ground. Okay, so you have to design the logic accordingly. Now let us look at the details and let us try to code or write a program to make the LEDs on or off depending on the state of the switch. So there are two inbuilt switches which are there in the TIVA C board, okay, and three inbuilt LEDs. We know that PF1 is red LED, PF2 is blue LED, and PF3 is green LED. Now coming to the switches, PF0 is switch number 2, then PF4 is switch number 5. So if we write it like this, then D0, D1, D2, D3, D4, and D5. Okay, so D0 is our switch number 2 as W2, okay, which is PF0. Okay, and then we have the red LED, then we have the blue LED, then we have the green LED, and then we have the switch number 1. Okay, remember switch number 2 is a D0. So switch number 1, and then we have the PF1, PF2, PF3, and PF4. So this is the connection for the switches and LEDs. So just make a note of this thing, and then this is also provided in the table 2.2 in the main manual of the TIVA C board. Now we are going to talk about the switches, and rest we know how to make the LEDs on or off, or what kind of logics we need to design to make the GPIO F1, 2, and 3 high or low. So what are the sequences that we have to remember or follow to make the LEDs on or off depending on the state of the switch or event of the switch? So event or state of the switch. So first of all, always remember, if you are going to use any peripheral, be it GPIO, timer, ADC, DAC, whichever peripheral you are using, you always have to enable the clock for that particular peripheral. Okay, remember, this is the first stage for any peripheral that you use. So provide clock to the peripheral. So here we are using the GPIOF. So we'll be going for the system clock which activates GPIO port F. May I know the name of that particular clock which activates port F? Or which register we should use to activate the clock on GPIO port F? The name of the register.
RCDC GPIO.
Right. So on the background, please open the manual, okay, or the data sheet, RCGC GPIO. Okay, we'll be using this particular register, and then first of all provide the clock, and only after that you can use whether you want to use the switch or whether you want to use the LEDs. So you have to provide the clock first. Now coming to one important factor when we are saying unlock GPIO pin. Okay, why we need to unlock the GPIO, what unlocking is, and why it is required for that. So this is our GPIO register. Okay, so GPIO clock is provided by RCGC GPIO. But here, if you slowly scroll down, okay, not here. Okay, I will just open the data sheet. I'll show you there. So we have the data sheet here. Okay, in that, first you go to the GPIO register map. Okay, now let us go through the details. Here, when you scroll down in the register map, okay, slowly when you come down, Now here it says important, the table shown below shows special consideration GPIO pins. Most GPIO pins are configured as GPIO and tri-state. Tri-stated, that means very high resistance by default. But GPIO AFSL, GPIO DEN, GPIO PDR, PUR, GPIO PCTL by default will be 0. That means whenever you reset the system, all these registers, these 5 registers in the GPIO will get a value of 0. Second, special consideration pins may be programmed to non-GPIO functions. When we say GPIO function, general purpose input output. Okay, general purpose input output. But apart from the general purpose input output, each pin has got multiple functionalities on it. Depending on the choice of the designer, he may use the same pin for maybe normal input or output, or maybe for ADC, DAC, or some other functionalities, provided that pin have that particular function. For that, I remember once I showed you this particular image where, wait a second, not here. Okay, this image I showed in the very beginning of the discussion about TIVA C board, and you can see here, if I zoom one particular area, for example, this is the GPI, these are the pins which are provided by the TIVA C board. And now if you go through these pins, for example, the yellow pins, all these yellow pins are digitally enabled or disabled. So you can make it digital IO. For example, here you can make it digital read or digital write ports, all these yellow pins. Apart from that, these yellow pins can do another functionalities also, like the green one, analog write. So whichever pins are green, okay, for example, here, okay, pin 4, PE4 can be used as a digital input output, or apart from that, it can be used for analog write purpose. And now here the same pin PE4 can be used for analog read also. So if you see here, yellow, blue, green. So blue is analog read, analog write, or digital IO. So this PE4 can be digital IO, can be analog read or analog write. Apart from that, the same pin can be used for SCL, okay, serial clock, which is used for SSI communication or SPI communication, okay. And you can also use it as a RX, that means receiver pin, if you are using the pin for UART purpose. That means the same pin can be used as a digital IO, or it can be used for analog IO, or it can be used for providing the clock for SPI communication, or it can also be used as an RX pin for UART communication. So before activating or using any of these pins, you must declare what kind of utility you are going to take from these particular pins. Okay, so now coming back to the data sheet. So here you can see PA1 and PA0. So PA1 and 0 by default are for UART 0. UART means serial communication 0. Okay, and then PA5 2. Okay, PA5 to 2 are for SSI 0. That means SPI communication 0. So because there are multiple SPI communication supporting. For example, this is SCL2, SCL3. Okay, so there are 3, 0, 1, 2, 3. That means 4 different SPI communication modules are available for you. Okay, so you can connect 4 separate SPI communication based modules with this particular microcontroller board. These modules can be used for RF communication, that means wireless communication, or wired communication. It is your choice, but we will might not be possible to show all these things in the course. But this can be used for communication purpose also. So now the problem here is these pins, for example, PA10, we are not that much worried about these pins because we are not going to use these pins right now. But let me show you one important pin which is actually creating the problem for us. That is PF0. Why PF0 is creating the problem here? Because we have seen, okay, just a second. Okay, we have seen that PF0 is connected to switch number 2. Okay, so that is the issue here. And we don't want to use that pin without knowing the full details about that pin. PF0 is the pin which is by default not allowed for GPIO purpose. Or which purpose? When you are using it as a switch, you will have to use either pull up or pull down. So these are the two functionalities which are used with the switch. So to activate those functionalities, we will have to go through some important details. Which are those details? For example, here it says A, for example, GPIO A. Here, this particular block, okay, to the power A. So this pin is configured as GPIO by default. Okay, by default it is GPIO, but is logged. So this line is very important. Though it is a GPIO, it is logged. So you cannot directly use it and can only be reprogrammed by unlocking pin GPIO LOC register. So you have to use GPIO lock register to first unlock it, and then apart from that, and uncommenting it by setting GPIOCR commit register. So now I believe you may understand, or you might have got this meaning why we need to unlock this particular GPIO pin for the switch number 2. Why? Because switch number 2 is connected to PF0 and PF0 comes under this particular situation. That is, it is logged by default. So first we have to unlock it, and then we have to use commit register to use any functionalities. Why? Which functionalities we are actually going for, or we are looking for? Pull up or pull down functionalities. Okay. So anyway, if you have to program PF0, you have to unlock it and then use the commit register also. Okay. Done. So let me just go through this particular page. Now, if you go through this particular register, GPIOLOCK Register, okay, register number 19 in the GPIO registers, it says GPIOLOCK Register enables write access to GPIOCR. So you cannot write on GPIOCR register until unless you activate or you modify this GPIO lock. Remember, for that we need to write 4C, 4F, 43, 4B in the GPIO lock register. This is a number which we have to remember. You cannot write any other number to unlock the GPIO lock register. So to unlock it, okay, you always have to use 4C, 4F, 43, 4B. This number has to be written to the GPIO lock register. And if you write this number, then GPIO lock register gets unlocks. and then you can change the value in GPIO commit register. Okay, so remember this number 4C 4F 43 4B, this number, this is required to unlock the GPIOCR register, which we can modify it, and until unless we have allowed the GPIOCR register, we cannot use PF0. Okay, so in the program we will see all these lines there, and then at that time I believe this confusion will not be there. The commit register, use of commit register. Commit register is CR. Okay, the GPIO CR. So the commit register is GPIOCR. Okay, so once you have written that number 434C 4F 4B, okay, on the GPIO lock register, then you can write on the GPIO commit register. What is there in the GPIO commit register? Why we are actually interested in GPIO CR register? Now, in the CR register, we can see here there are 8 bits which are allowed to be changed. 0 to 7, 8 bits. What is the utility of these 8 bits? So bit number 7 to 0 is CR. If you make it 0, okay, wait, let me check if I can put something on that. Okay, here. If you make this any particular pin 0, then the corresponding AFSCL, PUR, PDR, or GPIO DEN bits cannot be written. So if it is 0, then you cannot write anything related to pull up register, pull down register, okay, alternate function select register, or digital enable functionalities. So therefore we have to write 1 in this particular bit position to make that particular bit high. So we are interested in the 0th bit of the port F. So port F, this is, sorry, not this is AHP. Okay, we are interested in APB right now. Okay, so this is our register 4002 5000, and then after reaching here we need to go through the offset, which will take us to GPIO CR. Okay, offset is 524. So 4002 524, we will take, it will take us to this particular register, and in this register we have 8 bits. We will make one of these bits 1, especially the 0th bit 1, so that we can use pull up or pull down functionalities. Done. So till this part, anyone having any difficulty in this part? Because then after that everything is simple. Why we need GPIO lock register, and why we need the CR register? Any doubt till this part? Anyone having any doubt in this part? Okay, let me just draw a small diagram so that will make life more easy. Look, we have the port F. Okay, port F0, which is connected to our switch number 2. Clear? This is our first thing. But we cannot directly go and write on this particular PF. So first thing, because PF is part of the port F, so first we need to provide the clock to the port F. Okay, so this is provided by the RC GC GPIO. Okay, this particular register will enable the clock in this port. So now the clock is active. We have, if we go through the GPIO, okay, and then activate the clock. Then after that we have to read the status of switch, and because we want to use internal pull up, okay, pull up of the switch, we need to activate some functionalities. But we go through the data sheet and we found that PF0 cannot be altered directly because it is logged. Okay, this pin is basically logged. So to unlock it, we need GPIO lock register. Okay, first we will enter some number which is 43, I think 434C. I don't remember now. 434C 48 something like that. 4C 4F 434B. Okay, so this number we have to enter anyway. Okay, gone. My goodness. Okay, I'm not going to draw it because it is gone. So anyway, I hope you understood it. So we have to write it on the CR register to use the functionalities of pull up or pull down. Okay, then of course the same routine job which we were using to make the LEDs on or off, that is define the direction of the LED which is output. Then you can activate the internal pull up or pull down register for the switch, and then digital enable the pins for the switch and LEDs. Digital enabling, we know GPIO DEN. Pull up register is PUR. Wait a second, this particular register is PUR, GPIO PUR, and then DEN, GPIO DEN. So we have used GPIO DEN in the past also. So we will have to go through these 6 steps and write a program to read the switch and then make the LED on or off. Okay, so let us go through the project. The most important thing about this project is reading the switch. That means we have to, if it was not about PF0, then we will not have to worry about the lock and CR register. But because we are interested in the PF0 also, so we are going for the lock register. Okay, I have provided you the header file. So this is the header file. Okay, and we are going to use this header file. No, I have not provided you the structured header file, right? Please cross check it. That there are 2 different header files. This I have not provided you. Okay, let me give you the header file so that it will make your life a bit easier. Structured header file. Okay, CMSIS later I will discuss about it. So in the classroom I am going to share the structured header file for TM4C123GH6PM. Okay. If needed, please write the code along with the header file. Okay, because the header file which I provided you in the past was not structured. And during the lectures, we have discussed about the structure, why we need structures, because structure can contain different data types, and all these different data types are arranged in the fashion of arrays. You know, arrays have same data type and memory is allotted in the consecutive manner. Structure, on the other hand, has got multiple, it can have multiple different data types, and but have the property of arrays, due to which all these variables are arranged in the memory in a consecutive manner. So let us just briefly see the header file to understand the difference here. Okay, so this one is my structured header file, and then other one, let me show you, using bare registers, this one. So I have previously shared with you this kind of register, header file, where you have all the registers which are mapped to a particular address. So we will be we were using this particular register as to dereference the value in that register to enter some value in that. Clear? But whereas now there is a difference. For example, view, if I show you the difference here, line numbers. Okay. Keep an eye on the number of lines. This particular header file has got somewhere on 10,000 lines. Okay. Why? Because each and every individual port, for example, here, port C is properly defined, then port D is completely defined. Then after that, you have port E and port F, which is coming after this. Okay. Port E, totally defined memory wise. Then you have port F, which is memory wise. But because we know that all these registers are arranged in a sequential manner. For example, you can see 3FC 400 404 408 go up, 3FC 400 404 408. So we are repeating the same thing again and again. Whereas in the header file which I have shared with you now, it has the structures. What is the benefit of structure? For example, GPIO A type, that's all. So it covers all the GPIOs. So whether you need GPIO A, GPIO B, GPIO C or whatever, here these are arranged in a particular manner. And whenever you use GPIO A or B or C or D or E or F, these particular structure is repeated again. So where is the details for this particular, like for example here, this is the structure definition, type def structure, which we have also discussed in our lecture. Then curly braces, then all the elements in the or the members of the structure and the name of the structure, GPIOA. It is the name. And now when you come down, okay, come down and you can see here, they have defined all the base addresses and corresponding the offsets and everything, and you don't have to worry about that part. They have arranged it in a very proper manner, because it is always repeating. You don't have to repeat them again and again. So you just have to call the structure name, and then it will give you the variables which are available or members which are available in that particular structure. Okay, so what is the benefit of using this particular header file? For example, in the past we always used to go to the header file, copy it and paste it. Where now in this case, for example, if you just type GPIO F, okay, then because you are using structure, you can use this particular symbol, minus sign, and then an arrow or greater than a symbol, and suddenly it lists out all the registers which are available with that particular peripheral, be it GPIO, be it ADC, DAC, whichever. For example, now we know that RCGC GPIO is a part of system clock. So you just type sys ctl and then see here. It lists out all the clocks which are available for different peripherals. All the peripherals. Okay. So now if I am interested in GPIOF, GPIO, or sorry, RCGC, you can just use RCGC. So RCGC 0, 1, 2 or RCGC, you have to use this arrow, sorry, RCGC GPIO, and then after that you can write your own code. So this actually helps in reducing, or you don't have to go to 2 and 4th with the particular header file. And this will be helpful in understanding the CMSIS also. In future we will be using that part. Okay, so first of all, remember, now from here onwards use this particular header file, because you can take the advantage of this particular symbol, okay, minus sign and this, and it will automatically list all the registers which are available, and then you can enter the value in that particular register. Okay, so done. So we have introduced a new header file which is structured. So when we have a structured file, then in that case you can use the members of the structure by just using the GPIO FB, whichever component you like. For example, SSI 0. Okay, SSI 0 type. So SSI 1, 2 or 3, whichever you want to use, you can use it that part. Similarly, UART 0. There might be 3 or 4 UART. So UART 1, 2, 3, you just have to write that part only. For example, UART 0. Okay, see here, it all automatically listed all the registers which are available with the UART. Okay, so this will further reduce the pain of writing driver files. Okay, now first of all, what we are doing, I hope you have the data sheet with you. So system clock RCGC 2. Instead of RCGC 2, you can use RCGC GPIO also. Why I am using RCGC 2? Because RCGC 2 and RCGC GPIO both are same. Okay, you can see here, these are a bit in-depth things which are not that much required for you guys. Anyway, so RCGC 2. So here you can see here RCGC 2. Okay, let me just, both are same. Okay, anyway, you can use RCGC GPIO also. Okay, let me click on the RCGC 2. Here it says automatically that this is the clock gating for the GPIO also. So here you can see GPIO F, E, D, C, B, A. So even you can activate the clock from RCGC 2 also. Okay, for the GPIO pins especially. For example, here you can see 5 number pin, port F, clock gating. So this bit controls the clock gating of port F. If set, the module receives the clock and functions. Otherwise, the module is unlocked and disabled. Okay. So you can use RCGC2 or RCGC GPIO also. RCGC, wait. One more benefit is that RCGC GPIO. Okay. One more benefit is that you can use a shortcut. Okay. For example, if I am going to use the shortcut, then you have to just press Control and space. It will automatically show you all the possibilities. For example, I just typed S. Okay, and then Control space. So it lists automatically, it will list all the things which are there. Okay, so now if I need sysctl, then press tab, then this sign, it will automatically start giving up all the possibilities that you want to use. Okay, so RCGC GPIO, then tab, done. You don't have to copy paste all the things again and again. Okay, now here we are entering 20. We know that this will enable the clock. Why? Because 20 means 0010, then 0000. So that is D fifth bit, and D fifth bit is port F. Done. This is used, I have discussed it, because to enable the writing on CR register. So you have to enter this particular number. There is no alternative. So 4C, 4F, 43, 4B. Okay, to unlock the CR register, because CR register contains the benefit of pull-up register, PUR. So please, while I am explaining you, keep the windows separate. Okay, by just clicking like this, and you can keep this window like this, and then you can try to type the program along with me. Okay, so This way you can directly check what the things are doing. Okay, so GPIO port F CR register, we are enabling the commit register for PF0. Okay, PF0, because we are going to port F's commit register and we are making it 1, the 00000001. Okay, so this one is for the PF0, to which the switch number 2 is connected. Okay, and then we are enabling the pull up register. Okay, so it will be 00011000. So we are enabling the pull up register. Now then after that we are telling that these two codes are same. Okay, that PF1 is your output. Okay, 0002, I hope you remember this number. Which LED we are focusing on in this case, this particular bit?
Red LED.
Red LED. So remember, 02 will enable the red LED, or we are making it red LED's output. If you make it 4, then it will be your blue LED, and if you make it 8, it will be the green LED. Okay. Then after that, we are making all the pins digitally enabled 1, 2. Okay. So 1, 2 means 0001, 0010. Okay. So this is our LED, and here we have the switch. Okay. We have enabled the digital enable. So it will be making digital read or digital write. Digital enable means only digitally enabling it. For digital read or write will be defined by the DIR register. Okay. Now let us go down, and this part, what we are doing, we are reading the GPIO data register, and we are multiplying it with, or bitwise anding it or masking it with 00010. That means, is it 1 or not? So if this particular multiplication results in 10, then we can say that the bit the switch is pressed, otherwise the switch is not pressed. Okay, and that state is taken into this particular variable switch state. And then what we are doing, if that is becoming 1 or it is greater than 3u means again 0011. Okay, so we are complementing the red LED. By default it will be the whatever is the state that you are reading. Because why we are complementing it here, the switch state? Because the switch is connected towards ground when it is pressed. Remember, when the switch is pressed, it is connected to ground. That's why we are just making it opposite. Okay, this part, when the switch is pressed, it goes to ground, it is not going to high value. Okay, so now, okay, this particular done. And with this, this particular loop will keep on repeating. It will check the state of the switch, and then it will make the LED on or off. Done. Okay, so this is how you can read the switch. Only thing that you have to keep in mind is the PF0. Okay, for that you have to use the commit register, and to use the commit register you have to use the unlock register. And in the unlock register we have to enter a number which is specified in the uh, data sheet. Okay, now coming to CMSIS. Okay, what is CMSIS? Shall we talk? Okay, it will make your life easy when you are going to write a program. What is CMSIS? If you go to the Google and just type CMSIS. Okay, so this is a standard or a group which is actually controlling or which is writing driver files or libraries for ARM Cortex or ARM microcontrollers. Okay, so it is known as Common Microcontroller Software Interface Standard. Okay, what is the benefit of using this particular technique or this particular standard? What is the benefit? Look, the benefit is we know that Cortex M4. We are talking about all this about Cortex M4. Okay, and Cortex M4 architecture is followed by many vendors. Like right now, we are talking about Texas Instrument. There is another vendor, STM32 or STM group, and then we have the NXP and so on. Apple, Samsung, they are all using this particular architecture. Architecture is a different thing. Apart from that, the registers which they are using are different, because in the beginning we talked about the memory allocation and the way the memory is arranged in the ARM Cortex, the 4 GB memory which is provided in this particular microcontroller. There is a vendor specific memory region also, where the vendor can specify different registers and the behavior. So now the question is, when suppose a person is writing a code for TI, okay, and he developed a project using Cortex M4, and like I said, Cortex M4 has got a very big family. Now tomorrow the company said, okay, TI's microcontroller is done. Now we need STM microcontroller because it has got few extra timers in it. Although it is following the same Cortex M4 architecture, might be possible they have some peripherals less or more. Now the programmer will be having a very difficult time to write the same program for STM based microcontroller, because the registers are different, the memory allocations are different, interrupts are different, and so on. Now the question is how he can easily switch from one microcontroller or one vendor to another vendor in a very simple way. For that, he can rely on CMSIS, because CMSIS produces vendor independent libraries. So it will help you to switch from one vendor to another vendor to another vendor just by following the CMSIS files. Okay, so let me just briefly elaborate about this particular thing, because it is not necessary that you always work on TI based microcontrollers. So this particular the standard, so CMSIS is a vendor independent abstraction layer of microcontrollers. Only this thing you have to remember. Okay, rest about the things you don't have to worry about it, and we are not going to talk too much about the CMSIS, but of course it will help you to simplify your life. So CMSIS is a vendor independent abstraction layer for microcontrollers that are based on ARM Cortex processors. Done. So these particular CMSIS, they provide you all different libraries for different Cortex M family, Cortex A families, DSPs, RTOS, and everything. So it actually simplifies your life when you are changing your microcontroller from one vendor to another vendor, because otherwise it will be very difficult to write a program. So that's why I'm actually moving from the very bare minimum, that means the register level programming, to slowly we are coming to a stage where we can write more better programs using some libraries which are predefined or which are standardized by some companies, so that it will help you whenever you go to any other company or when you are taking a professional career in embedded system. Then you can take help of these technologies to simplify your life, because you are not going to work with Texas Instruments microcontroller everywhere. Okay, so ARM, okay, supplies CMSIS core template files that are supported, that support Cortex M processors. I showed you Cortex M, Cortex A. They support almost every types of microcontrollers which are produced by ARM. Okay, and of course, ARM nowadays have almost 95 to 98% market share. So you don't have, you most of you will be working in the ARM architecture itself, be it in Apple, Samsung, or any other company. So CMSIS will help you to simplify your life, and you can develop more better projects using CMSIS core. Okay, what are there in the CMSIS based files? So they provide you the files which contains register names of the core peripheral like Cortex M4. So they will provide you the list of registers and all the things in the file. And apart from that, they will provide you the details of all the exceptions. Whenever we are saying exceptions, it is about interrupts also. Okay, so exceptions and interrupts. If you recall, there are 15 exceptions and then 240, somewhere around 240 interrupts are there, and exceptions somewhere around 15 exceptions are there. We have discussed about this in the very beginning, how the NVIC nested vector interrupt controller helps to manage this matrix. Okay, apart from that, they provide you functions to access core peripherals. So they provide you the functions also, and special CPU instructions also. CPU means microcontroller based instructions also. They provide you almost everything. Apart from that, they provide you the startup code. Okay, till now we are using header file, remember. Okay, we were using TM4C123 GH6PM dot h file, and this was actually used to check the registers and then write the programs. But we were not using startup code or startup file. So what is the difference between a simple header file and a startup file? I will show you that. So that means the CMSIS provides you the startup code also, or the startup file also. Apart from that, it gives you the freedom to design or configure the system code. Okay, so now along with the .h file for the device or the microcontroller, they provide you some extra features, like they provide you the startup file. I will show you what is there inside the startup file, and along with that, they provide you the system file. Okay, by which you can configure the whole system or change the way the system works. Okay, what are there in that? Let us check. So we can go to the system sys. Okay, so remember, we are discussing about CMSIS version 4, but of course there are more latest versions like 5.8 and all. For example, if you go to CMSIS latest version, okay, you go to core M, and then you can see here the core M, and then you go to templates, and here they will talk about the version. So CMSIS version 5.5.0, I think it is the latest, or 5.8.0. I have to check. Anyway, so in this, they provide you the template about what are the files which are there. If you have any doubt, please do ask these things, because these are not very simple or very standardized kind of things in which you can get all the details from the internet or all. Because what I'm discussing here is a bit complicated, but it actually, if you know these things, it will help you in your long term. So Cortex M or CMSIS has got many versions. We will be discussing about version number 4. There is a reason for that. Okay, anyway, so what is there inside that? So all the CMSIS contains general core, driver, DSP, NN, RTOS version 1, RTOS number 2, packs, build, SVD, DAP, zone. These are the tabs which are available and which is In the past, they were not that much. So we will go to the core and we will go to the template files. So what are there inside the template file? There are three different types of or categories of files. Okay. So what are these three categories? You can see here. One is the blue category. Then you have the gray category, and then you have the purple category. Okay. So the blue category is provided, or they are vendor specific. Whenever we say vendor, remember it can be Texas Instruments, STM, NXP, or any other company. Okay, so these are vendor specific core files. Apart from that, you will get user program. So whatever you write, the C.C file that you are writing is the main file. Okay, and then you have separate four files which are for the core, that is for the ARM Cortex M4. So when you use these three together, then after that, if you make a project using these files, then it will be used. It can be, that program can be used for any other vendor also. You don't have to depend on the vendor specific things. You can easily switch from one vendor to another vendor because you are using CMSIS core standard files also. And now if you see here, they have simplified in the version 5.5.0. Now you have four vendor specific files and two the core files, and then one file which you have to write by your own, that is the main file. Any doubt till this part? What is CMSIS? Why we need to discuss about CMSIS? What are the things that we should know about CMSIS? Anyone having any doubt? Anyone having any doubt why we are moving towards CMSIS? Sajal Pathak. Hello, Sajal, are you there? Okay, Piyush, are you there?
Yes, sir.
Why we are moving towards CMSIS?
Sir, so we can, if we use different vendors, so we can easily switch between the languages.
Okay,
Uh,
so yeah, you can use the same program for a different vendor's microcontroller, provided you have the same core, that is Cortex M4 or Cortex M3 or Cortex M0 or whatever.
yes,
Okay,
sir.
so what I have done is I have I have made a simple folder which contains all these details. Later I can show you how to retrieve these folders and everything, but right now it is not that important for you. So what I have done is I have made a folder which contains all the CMSIS files. Okay, just a second. Let me, no, no. Here files. In this, I have CMSIS files. Okay, I will share this particular files with you, and please, in 15 minutes, I will show you how to use these files and then create your own program. Okay, so I'm just making it CMSIS files. Okay, then I will share it with the classroom. And later, if anyone is interested to know more about this, how to find the CMSIS files and everything, then can consult me personally. CMSIS files, okay. PFA. Okay, then I can just go to CMSIS files, drag it, drop it. Okay, posted. It is not that difficult to find these files. Later I can tell you how to get these files anyway. So if you open this folder, okay, if you open this folder, I have created two folders in them. One is the blue files and the other one is purple files. Why I'm calling it blue files and purple files? Because if you go through the CMSIS template, there are some blue template files. And if you check here, the name startup underscore device dot s. So wherever the device word is there, remember it is about TM4C123GH6PM. Okay, that is the device that we are using. So startup underscore device dot s. So let us go to the blue folder, and inside that you will be able to see startup tm4c123.s file. That is the startup file. Apart from that, you have system underscore device dot c file. That is system underscore tm4c123. That, so go to the in, that means include file, and there you can see system underscore tm4c123.h file. Okay, then you need device.h file. Of course, device is tm4c123gh6pm.h file. Okay, then you need system underscore device.h file, that is there. Okay, so we have that file here. Now coming to the core files, so which are there inside the purple folder. Okay, so go to the purple folder, and then you can see here include core. I have made a name, or I have given a name to include core. Okay, in that you can see all these files which are the core related files, like core underscore cpu.h. Okay, so core underscore cm4.h, then core underscore cm, that means CMSIS instruction.h, instr instruction.h. So here is that file, and similarly cm function.h, func. Okay, so you have all these files. I have made a folder in which you have all those files. Okay, so what you have to do from here onwards, if you don't have any confusion, I have made a readme file also, which you can use and to understand what you have to do. And let me show you what you have to do. Okay, I have 10 minutes with me. From here onwards, whenever you are going to make any project, okay, I will just close the workspace, close workspace, no to all. Okay, and just keep an eye what I am doing here. Okay, so first of all, you will go to the project, create new project, C, main, and we always used to do this job. Okay, for time being, I'm going to the desktop and I'm making a new folder, and I'm going to give the name delete it, so that I can delete it later. Okay, and inside that folder, I'm going to make a project, IAR project, which is test. Okay, save. Now it will make a project named test in the desktop. Okay, so I will have to go to desktop also, right click, new window. Okay, so here in the desktop I have folder delete it, where the project is getting ready. Let the project finish. It is taking too much time. Anyway, done. Okay, so this is my main.c project, and then if I want to make it, I can just click make, and then I can give a name. For before that, let me go to the, before continuing with the project, I want to include the CMSIS file with this project, so that I can switch to another vendors if needed. So to enable that feature, what I will need is, I will go to the folder. In the folder, delete it, we have debug, settings, main.c, and test the project. Okay, so first I will open the blue folder. Okay, copy all these files, except the readme. Readme is not necessary. So include source and startup underscore tm4c123.h. I will take these three files and paste it here. Done. Then I will go back. In the Perfl files, I will take this include core, Control C, and I will paste it here. I'm showing you the simplest way to make the project. Okay, so we have added three new folders, include source and include core. Apart from that, we have added one startup file, startup tm4c123.s. Now come to the project, right click, go to options. Okay, in the options you have to select the device. So go to st, no sorry, Texas Instruments, tm4c, come down to 3gh6pm. Okay, the microcontroller has been selected. Now coming down, you can go to, wait a second, no, C++ compiler. Let me just preprocessor. Okay, so you go to C++ compiler, preprocessor, and then you have this button. Okay, click on that. Remember how you are getting there. First you went to the general, you selected the microcontroller. Then after that, come down to the C++ compiler, go to preprocessor, click on these three dots, click on that, and then click add. Okay, and then you have to add two files. One is this inc. Done. Click another time and go back, click include core. So these two folders you have to include. Done. Okay. Okay, and then you can just make it okay. And after that, you can go to right click the project. Okay, it is taking time, I think. Still taking time. Okay, go to project, add files, startup underscore tm4c123.s. You first add that file. Okay, you have added that file, the startup file. Then right click again, options, sorry, right click, add files, go to include system, no, wait a second, src, this one, system tm4c 123.c file. Okay, okay, open. So now you have added the startup file and system tm4c 123.c file. These two files you have added. Done. And now after that, you can just write include, sorry, hash include. We know what we have to include. So tm4c123gh6pm.h. Okay, done. And then make the file. Then give it the name. Okay, I will give the name test. Save. Done. So no errors, no warnings. Okay, and your CMSIS related project you can start writing now. For example, if you see here inside the tm4c.s, you have the file called object file. In the system tm4c123.c, you have all the core files. Okay, apart from that, you have the tm4c123gh6pm header file also. Okay, so you can double click on that and you can see here the header file is along with you. So now you might be thinking why I need the header file, this particular header file, and why I need all these things to go through that. Okay, this we can discuss in the next class, why we need CMSIS and why we have these things. Apart from that, now you have all the same facilities. So sys, so might be possible in the very beginning it will not work. I will just close the project, don't worry. Okay, I will make it. Let me try once again. Sys, no, it is not. Okay, close it. Wait a second. Okay, close it. Yes to all, and reopen it, because this is one issue with the software, I think. Okay, I'm reopening the project from the delete it folder, and then I can write sys control space, and you can see all the drivers are available, all the registers are available, RCGC, GPIO. Okay, or equal to whichever you want, you can use it. Okay, or equal to or equal to 20h. Okay. Okay, so in this way you can use all the registers. GPIO F, sorry, not F. Okay, F, you can go to this, then will automatically show you all the registers whichever you want. So remember these 4 or 5 steps, and then you can write your own CMSIS project, and this will simplify your life in future. Okay, those who are interested to know how to get these CMSIS files, where these are located, and how to get it downloaded, or all those stuff, we can discuss it separately, because that is not the part of the course. Okay, from the next lecture, we will be using CMSIS header files to make our projects. Okay, so please practice this once or twice, how to get into the CMSIS and include the files and start writing the project. If you have any doubt, you can ask me in the next lecture. Okay.